Hello. Hi. It is currently 2:38 a.m. I'm gonna try to do this because I don't have time tomorrow to do it. So I'm gonna do it today. So, just to clarify, everyone, this is the statistics one. This is for Econ 05. Just so you guys know, here is my stuff. Okay, so let me try zooming in on this. There we go. Okay, as you can sort of see here, I've done stuff for number 1, I've done stuff for number 2, and I've done stuff for all the remaining ones, okay? I have all my workings out here, okay? But I'm just going to essentially go over everything, just to make it all clear. And yeah, we'll just go through everything bit by bit. I should do chapters again, just to make it a little easier. Okay, so I'm just going to put that over there, and we're going to bring in the paper. Okay, all good. Okay, let's zoom in back again. As you can tell, my nail polish has deteriorated. We may be having performance issues. Well then, that's nice to know. Okay, so let's go over everything. One moment. Let's just pause the recording. Oh! Pardon me, I just returned from the dark abyss. What an experience. Anyways, I've got the text up here, so we'll go over it. So, first of all, let's go over number 1. So, oh, hold on. I think it's a little overexposed here. Hopefully that should work. Oh, that looks a little better. Okay, so for number 1. So now what it's saying here is read the section of the course textbook on the Poisson distribution. So it should say that there. Hopefully you guys should have the paper open. Then it's saying, think of an example of a count variable which might follow a Poisson distribution. Okay, so it's giving us the example of number of major earthquakes or number of pieces of mail. Okay, so essentially, what a count variable is it's a discrete variable. Discrete. Okay, and it's essentially, yeah, it's a count variable is like something you can essentially count. Fairly easy, right? So, and also for a Poisson distribution, it has to be within a certain amount of time. Within time frame. So anything like, I don't know, car crashes in a day, something like that would be a random variable. Because this is a count, you can only have a discrete amount of, variables of that. You can't have 2.5 car crashes. And it can happen within a day, essentially. So, car crashes within a day. Now, I recommend you suggest one which you can get data on, okay? You can also do car crashes in a year if that suits you. But essentially get data that you can actually, work with, because that's going to be important later. Okay, then we go on to the next one. We have collect some observations on the random variable from part A. See what I meant? We've got to have something we can measure here. So, just to do a brief little intro, I did my phone calls going through my phone. Okay, and just so you guys know, okay, let me zoom in quickly. Is that good? That's pretty alright. Let me go up. You can sort of see my little distribution here. So you can see with the black line here, I wonder if I can actually use my pen as a pointer. Will I be able to? We got that, yeah. So you can see here, this black line going down like this. This was the real value I obtained. So I got a maximum of 0 calls per day because I'm lonely. And then it drops sort of exponentially, as you can sort of see this sort of drop here. The Poisson distribution, after calculating the mean, gave me this, which isn't exactly accurate, but that's for C, okay? Now for B, it explicitly states, collect some observation, what is the average observation in your data? When it says average, as you can see here, the average observation for me was, lambda equals 3, because I had 298 calls in 166 days. Kind of weird that it matched perfectly. Oh, I am not good for comedy. Okay, so essentially what happened there was that I took the mean of my entire data set, so it's the mean, remember, not the median. So I took the mean of my data set, and essentially that allowed me to get my value of lambda, and that will make sure what you go for your Poisson distribution. So say we had, I don't know, no, let's not do a sample, but say we had something with a mean of about 6. This is going to be equal to lambda, and we would draw this something like that, you know, where this is going to be around 6. Okay, make sure you possibly do this even in Excel. Excel is pretty good for graphing out this sort of stuff, especially with Poisson distributions. So have a try, okay, and see how close it is. Now, if your data follows it quite closely, something like this, then you could say it reasonably follows a Poisson distribution, perhaps not exactly, but close. If your data is radically off, something like that, then you're going to say why it doesn't, okay? Normally, data doesn't follow a Poisson distribution if it's not entirely random. So for example, with my dataset, the number of calls wasn't entirely random. Sometimes people just didn't want to call me. Sometimes I had lots of calls to do in the day, which contributed to some outlier values. Again, these aren't all random. So state that it's not going to be always random. Okay, let's go on to number 2. Now number 2 is trickier. Because you've got a lot more mathematics in this. I'm going to try to walk through it fairly quickly because it's going to take a while. So you should be able to do 2a by yourself, but just for simplicity's sake, I'm going to do it again. Okay, you've got between 0 and 1 on the x-axis and 1 and 7 over 3. For the x squared, it's obviously going to go up to 1 again. I expect you guys to know this, you know. And then for the line, you're just going to go back down to 7 over 3. Pretty simple. Okay, I assume you guys should know how to draw this already. B here. Now, remember, the expected value, which we're going to call e of x, is calculated with the following formula. So you've got the integral, negative infinity to positive infinity, so basically all values, of x multiplied by f of x dx. Okay? And this is what it's going to be. Now, because we've got 2 separate sort of functions here, we're going to do it for both of them. Okay? So this is going to be equal to between 0 and 1, remember to keep those bounds in there, of x multiplied by x squared. This is for the first one, dx. And then for the second one, no, not equals plus. For the second one, we're going to do 1, 7 over 3. And then we're going to times x by, let me just check, what was the function? There it is. 7 quarters minus 3/4 x dx. Okay, I won't go through all the details because you guys probably know how to do an integral. Okay, I'm not going to go through it too much. But essentially what I'm getting is 131 over 108, or essentially 1.212962962963. That's essentially what I'm getting. Yeah, you guys tell me if you get anything different. Remember, I am not the final say. Okay, let's go on to C of that. Now C is a bit trickier. Variance requires a lot more calculations. So essentially variance of x is going to be slightly different. It requires the value we've just got here, 131 over 108. So essentially what it is, let me just check here. Yeah, there it is. Negative infinity to positive infinity, as always. And then we're multiplying the function by x minus the expected value. F of x dx. Okay, this one is much more complicated because, you know, there's much more of a function we're multiplying by. Plus we've got to put in that ex, which is going to be a little annoying. I would recommend you try to do this with, you know, your calculator. Do not do it longhand. It takes far too long. Try to do this with your calculator. Yeah. Essentially what you get after this is that I'm just going to write out the 2 integrals just so everything's clear. So you have 0 and 1, x minus 131, 108, x squared dx, plus 1, 7 over 3, x minus 131, 108 squared, as usual, multiplied by 7 over 4 minus 3/4 x dx. Essentially, that's the integral thing. Once you've worked it out, you should get something around roughly 0.18551097399396. Okay, this is what I got. Again, not the final authority, but this is what I've got. So the expected value is around 1.213, and then you've got var as 0.186 roughly. Okay, hopefully that's that for 2. Moving on to number 3 now. So for number 3, it's just a lot of calculations on after another. Let me show you guys how I do it. So I am using, and if you've done A-level, you're most likely familiar with this, I'm using a Casio FX991EX. This is the standard A-level calculator, so I expect you guys to already have that. If you don't, like if you've done an IB before coming here, this is a really good calculator. I am not sure if it's authorized by UCL, so do not quote me. This is just useful. So what I'm going to do with this, in case you've got this, I'm going to show you how to use it for distributions. You press menu here, and you get to this sort of screen here. Go down, or you just press 7 to go to distribution. And you want to pick here, okay, you want to press 2 and pick normal CD. Okay, this will allow you to set lower and upper limits, essentially. So, and there's the standard deviation, and there's the mean. So for this, we've got a standard normal distribution. We can just leave it as is, okay? A standard normal distribution with a mean of 0 and a standard deviation of 1. So we don't need to change it. It does, however, want an upper of 1.2. Z has to be lower than 1.2. Now, for the lower, 0 won't cut it because 0 is the mean. So we're going to essentially set a extremely low number. I know this isn't entirely great. Hold on, how well can you actually hear those taps? Let me check. Apparently they are getting picked up on the microphone. Okay, so essentially I've set a really low number. I've got upper, and then I've got, if you guys can see that, 0.8849303298. Okay, so let's write these all down just so you guys have a nice little look at them. By the way, sorry if I sound a bit tired or groggy. It's been a long night. Okay, for B, now for a probability where it is, where Z is larger than, okay, this is essentially going to be the probability of 1 minus the inverse, so Z is smaller than. So you always want to have it as the sum of all the smaller than probabilities, because you can use your cumulative function to do that. So in this case, it's going to be 1 minus 1.3, so I'm just going to replace this one with 1.33, and then that becomes 90, and then essentially we just go back to number 1, press 1 and minus the answer, we get, that's our probability. So for B, it is 0.09175913565. Okay, for C here. Lower than 1.7, we're going to go back to our distribution. The only annoying thing here is that it's been reset for us, so I have to re-put in my massive number again. There we go. That'll do. Honestly, you don't need something too big. Then it's asked for minus 1.7, so we're going to do that. Okay, and we don't need to change anything else, and we get 0.04 intriguing. That is correct though. Remember, these also correspond to percentage chances, so you get, this is going to be a 4.45% chance. So, and there we go. And we've got D, which is essentially going to be the same thing, we're just going to replace it with -1. And then we get 0.15865525539. What fun. So we've got 88%, 9%, 4%, and 15%. Nice. Now, for the next 4 questions, next 3, you can calculate them using this function here. Okay, it does work. So for example, 1.2, 1.33, that is correct. It is 23. Okay, the only problem is this isn't probably how they want you to do it. Okay, you can, for E, here, let me just write down E. So you've got probability, Let me zoom in a little more, just so it's a little clearer. Oh my. Is that good? I think that's good. You've got probability of 1.2 smaller than z, which is smaller than 1.33. Essentially, this is all values below 1.33 minus all the values below that. Okay, so this can also be phrased as z is smaller than 1.33 minus the probability that z is smaller than 1.22. 1.2. Essentially, this is going to take in all the values below 1.33, but above 1.2. I mean, we've already calculated this. This was so this was the answer on A. So for that one, so it's going to be, oh wait, no. Was it? It was. Oof. So we have 0.8849303298. And then we're minusing this, okay? So it's not going to be exactly this. It's going to be 1 minus this, because it's technically the actual not larger than function. We want the smaller than function. We wanted this, okay? But that's essentially, if we kind of backtrack, we'll get the other value, which is going to be near 90. Let me just double check it again. Give me one moment. What fun. I want to go to sleep so badly right now. Yeah, so it's about 0.90824088643, which gives you... And I'm going to do a manual calc on this. Technically speaking, I don't have to, but I'm going to anyway, just to make it sure. So we're getting 0.02331053455. Don't need to do anything specific with that, just work with that. Okay. For all this stuff, you do basically a similar thing. To be honest, as long as you guys know how to do this, okay, you know that logic, I'm expecting you to do sort of the same thing. The next few just are the same logic, and it would really take me a lot of time to just do it manually. So what I'm going to do is I'm going to skip doing that, because it's bloody 3 AM and I can't be bothered. So it's going to be between -7. No, that's -17. It's not even -7, it's -1.7. Dear me. So it's that. So it's going to be an 84% chance. So let's write that down, just so everything's a little easier to work with. Okay. And then we're going to essentially repeat this. So we've got -1.7 and then -1. This will be 11.4. Okay, so we've got 0.1140897912. So these are all the answers for 3, essentially. Essentially, 3 is just a lot of calculations. You've just got to get over it. Once you also realize this, I would recommend you write out your workings as this. So remember, anything like this is essentially going to be moving between things. Imagine it's sort of like a number line. So you have 1.5 up here. You've got 1.34, 1.33, 1.32. And then you've got some stuff like 1.23, 1.22, 1.21, stuff like that. So essentially, oh wait, hold on, I just realized it was 0. So it's 11918. So all the stuff in this range is going to be the stuff below 3, okay, so something like this, and then above 2, right? Above 1.2. So it's going to be everything in this range. What essentially this is it's all of this minus this. Okay? So it's everything below 1.33 minus everything below 1.2. And so that constitutes our little set. Okay, let's move on. So, for number 4, it is just a bit more difficult. Okay, so first of all, we have to define our probability distribution. We're going to say it as X is a distribution, a normal distribution. That N denotes normal. And we're going to write our mean and our standard deviation squared. So we have 12.2 as our mean. There we go. And then we're going to have 2.8 squared as our standard deviation. Okay. Remember that we're writing variance here, not standard deviation. You're able to write the standard deviation quite clearly here. Okay. So you could just go with that. Obviously, you don't need to write this out. So it's asking for the probability that x is less than 10, essentially. So what is the probability that it contains less than 10 grams of impurities? So hold on, let me read this out. So a company produces bags of chemical and is concerned about the impurity content. Oh no. It is believed that the weights of impurity... Oh my god, my neck. Not neck, my throat. My water. Dear Lord. Okay. So what's the probability that it contains less than 10 grams? Again, we can do this with a calculator. So we're going to go back in. What fun this is. We're going to reset our values because it's not a normal distribution. It's not a normal distribution. It's now a new one. So we have the upper set at 10, and we're going to keep the lower set astronomically low. So how was your day? Okay, so we've got that one, and then we get, voila, our probability. So it is going to be 0.216017446. Okay, now for the next one, we have the probability that it contains more than 15 grams. Again, as we saw with question 3, when you get more than 15 grams, we're essentially going to do a 1 minus the less than. Okay? Because that's an exhaustive set. More than and less than 15 is going to be the same exhaustive set of probabilities as before. Also, slight side note, when we talk about probability that x is larger than or equal to 15, and probability that x is larger than 15, they are essentially the same. This is because continuous probabilities, at 15, the probability is just going to be 0, that it's exactly that. Okay, so we basically define these two are essentially the same. Okay, so don't worry too much about equal than or stuff like that. They would be exactly the same. So we're going to do that. And what we're essentially going to get is, well, let's set it as 15. So this is the chance that it's lower than 15. Okay, so we got that, 8 point something. And then we're going to go back and minus that from 1, and we get 0.15. 86552539. What is the probability that it contains between 12 and 15 grams? As I showed you before, we can literally just use the function here to do it. But just to be frank with this, I'll just do this by longhand. So the probability that we've got between 12 and 15 grams is going to be equal to, remember, the probability of x is less than 15 minus the probability that x is less than 12. And then we've got that. So let's try it. So we've got less than 15. What fun this is, eh? So let's reset stuff. The annoying thing about this calculator is that it resets every single time, which is just always an annoyance. Just a second, I'm still recording. I am still recording. Huzzah! Right, so we get, for 15, oh, we had 15. Dang it. Anyway, we get 0.841344741, and then we're going to minus the 12 from it. So then we're going to check what 12 is. 12 is 4715283355. So that's our sort of calculation here, and then we essentially get, well, let's calculate it. So we had 0.841344741, I think it's. And then I'm just going to minus the answer because it's just the last thing I got, which was the probability under 12, this one. And then we should get the answer, which is, yeah, 0.3698164,106. Or essentially 37% chance. Okay, now when it's asking in D, how can we tell that it's closer without being able to sort of do any complex calculations? Well, let's think about where the mean is. 12.2. We've got 10 on this side and 15 on this side. Essentially, the one that's going to have the lower probability is the one that's furthest from the mean. This is only 2.2 from the mean, this is 2.8 from the mean. Okay, the further it is, the smaller the probability is. As we can kind of see here, 15 has got a 15%, and 10 has got a 21%. Essentially, the closer you are, the higher probability is. Okay, that's pretty easy to figure out, I think. Essentially, what the logic behind that is that it's uniform on each side. So it wouldn't, like, if I had something here to match an equal probability, it would have to be uniformly away from the mean. But if 10 is on this side, and then, 15 is further out here, then it's going to have a lower probability than 10, This is going to be 10, this is going to be 15. Okay, that's just how the graph works. Okay, and it's number 4 done. My throat. Ugh. Hold on, let me take another slug of water. Okay, let's get to it. So, scores on a test follow a normal distribution. What is the probability that a student will achieve a score that exceeds the mean score by more than 1.5 standard deviations? So, if we're going for the regular normal distribution, we're going to say z follows n with a 0 and 1 squared. This is just the normal distribution. Now, let's draw this out. Let's just make this a little easier. Okay. If we assume the center is 0, let's go for the normal distribution here. Okay. Now, for a student we've got 1 standard deviation here and 2 standard deviations here. So we've got a student that's roughly hitting around here. Okay. We don't really know what their probability is. The problem is, for most people, is that there's no value here. Okay. But thankfully, on something like this, where the standard deviation is 1, this is just going to be 1.5. Now, what is the question asking? Exceeds the mean score. So we are asking for everything above this. Probability that z is larger than 1.5. And as we remember, larger than corresponds to 1 minus less than. Less than 1.5. Okay. Let's go back in. Thankfully, the normal distribution is normally set up for the normal distribution. So I've got my mean and my standard deviation already set. What we're going to do is we're going to put in 1.5 for the upper, not with the answer. And then for the lower, we're going to do as negative as we can go. And that's that. We get, this is the chance. Yeah, so this is this value. Okay, we need to minus this from 1. And we get 0.06680720128. Okay, so it's a roughly 6.68% chance of getting above 1.5 standard deviations. Okay, all right. So that's the chance. Okay, final one. Number 6 now. Stay with me here, stay with me. So, we've got a new probability distribution. They've told me that the mean is 60, but we don't know the standard deviation, so we're going to call this one x again. We're going to say n is a probability distribution with a mean of 60, but we do not know the standard deviation. It's weird, right? We know it's squared at the very least, but shh. Now, okay, what we also know is that the probability of x is smaller than 75 is equivalent to 0.9332. Okay? Now, if you guys remember anything about sort of coding and returning things to the original normal distribution, you'll maybe recognize this part. If not, it's a little tricky. We recognize that the regular normal distribution is z with n 0, 1 squared, yeah? Essentially, to return that to original z, we do sort of this. X minus the mu, which is the mean, over the standard deviation. And this will essentially be part of z. So probability of z is smaller than that is going to be 0.9332. Essentially, this is what we've sort of replaced the 75 with, so it's going to be true for that. And what we get is z is less than, so for, let's say, our value at 75, yeah? So we have 75 minus 60, over the standard deviation, which should equal 0.9332. Okay? Now, for this, we need to use the inverse calculator. Again, this is a function of this, but if you guys can find this function anywhere else and share that with others, that would be much appreciated. Okay, as you can see here, I went to distribution again, and I'm going to select 3. Hold on, let me push this up. I'm going to select 3 for inverse normal. This gives me 3 slight possibilities: area, standard deviation, and mean. Okay, we know the area is 0.9332. We are setting the standard deviation and mean as their original values, because remember we have a normal distribution here, and what we get is 1.5. Okay, very close. So what we're going to say here is that this value here, 75 minus 60 of standard deviation, is equal to 1.5. You can sort of see where this is going now. So the standard deviation is going to be 1.5, standard deviations is equal to 15, which means the standard deviation is 10, meaning our distribution is n, 60, and 10 squared. There we go. Now, this is the end of the question. 4 students are chosen at random. What is the probability that at least one of them scores more than 80 points on their test? Now, probabilities can go like this. Say we have success and failure, you know. You could have 4 successes and no failures. You could have 3 successes and a failure, and this will follow binomial. So it's going to be... Oh, it's just going to have annoying stuff. But essentially, all we need to do is that sort of success-failure model. So we have 4, 0, we have S, S3, F1, S2, F2. We don't need to do any of that, okay? Essentially, all we're concerned with is the probability of all of them minus the probability that they all fail. Fail 4, essentially. So what's the possibility that they all fail? Well now, first of all, we need to figure out the possibility of more than 80 points on the test. Probability that x is larger than 80 points. Again, remember it's going to be 1 minus x is smaller than. So let me just calculate that quickly. We're going to go back to normal CD, and we're going to do over 80, no, under 80, pardon me. We want negative, no. Keep in mind, you could also do this the other way. This is just the way I choose to do it. All your choice, baby. And we're also going to reset the mean and the standard deviation for this question. What we get is 0.977 for this, and then we're going to subtract it from 1. What we essentially get is 0.227503132. So this is the chance that in a single circumstance someone gets over. It's a 22%. Okay? There's a 20... No, it's not 22%, sorry. It's 2.2%. Careful there. So that's the probability. Okay? The chance that they all fail is going to be the other one, right? It's going to be what we had before. 9.7. So this is the chance that they fail. This is going to be more useful to us, though. Okay? So essentially, it's going to be 1 minus this number here, 977249868 to the power of 4. Okay? And what that ends up being is it's going to be 1 minus that answer to the power of 4. And you get, let me just double check here, yeah. You get 0.08794194809. So essentially the chance that all 4, or well, at least one of them, sorry, the chance that at least one of them gets above 80 is about 8.8% chance. Okay. Thank you for watching. I'm sorry that it was still a bit long. I'm still hitting about half an hour. Hope you guys found that helpful. I am absolutely knocked out. Yeah, hope you guys have a good day, good night, whatever you're doing. See ya.